Okay, what we're depicting here is a truncated rectangular parallelepiped in white and a level plane intersecting it in green, okay? Now, that level plane intersects the top of this thing across here, right? So that if I project this down here, everything above this region in the plane, the initial truncated rectangular solid parallelepiped, okay, is lower than the level curve, right? And then everything on the other side, the original picture is higher than this level, right? Okay? Now, what we did with the model before, the probability of the quadratic function being factorable or having zeros corresponds to picture something like this. We had a surface and our z values were like x, y, and z values were chosen like in some range here. So like corresponding to this cube or cubic or rectangular solid, right? Between here and here. And those regions, the volumes of those regions corresponded to probabilities, okay? And for this region of this rectangle down in the xy plane, the curve represented by the original solid is lower than the level curve, okay? And then for everything else, it's higher. Now, if the original solid corresponds to the value of, and this isn't a good picture of it, I just drew it so it'd be convenient to see, to the z equals 2 square root of xy, which corresponds to this discriminant, right? And this level corresponds to your maximum possible value of your parameter A, okay? So we have this solid corresponding to, for example, A less than or equal to X less than or equal to B, and A less than or equal to Y less than or equal to C to B, and A less than or equal to Z less than or equal to B. That would be all the values of A, B, and C within this cube in this case. And we could have different values, different restrictions on A, B, and C, so it's not necessarily a cube, but it's easy to generalize. So we'll just assume it's a cube so I can talk about it as a cube. Okay, but this cube, or whatever it is, if we have different limits on X, Y, and Z, right? So these are possible values of our parameters for the quadratic. And I probably should not have used A and B here, because those are traditionally parameters of a quadratic function, A t squared plus B t plus C and so forth, right? So I probably should have used different letters here, but you get the idea. Right, we restrict ourselves in the space of possible parameters to some region, okay? So all our possible parameters occur in this region, okay? And this is the region where Z is 2 square root of xy, right? Now, part of this region here corresponds to values of x and y that give you a value of z, which corresponds to one of the parameters in the model, in the quadratic model, that would give you a positive discriminant. Part would be to a negative discriminant, right? Well, previously, I didn't really consider this line of demarcation and what all this means in terms of integrals, okay? So we want to think about that a little. I'm just going to toss that out as something to think about, okay? And then I'll probably phrase a problem in the, or question to interpret and think about without doing a lot of calculations. Because we're not ready to actually do the calculations, okay? For the real curve, this thing isn't a straight line, it's a hyperbola. It's a part of a hyperbola, so you have a region down here bounded by hyperbola. And we're not equipped yet to describe that region with inequalities and set up the integral. That comes in after we've completed chapter 4, which we're going to start today. Yeah, we're going to finish up chapter 3, start chapter 4, okay? So we're kind of anticipating something, so I don't want to go into too much detail on this. But the integrals I gave you last time don't really do what I said they do.
Find the volume, you mean? Or
Yeah, well, you can do an integral. You have a simple integral to find this volume, the volume of this thing, you know, the thing that this truncated figure approximates, okay? And it's really not truncated by a plane. It's truncated by that curve, z equals 2 square root of xy, right? So I'm just approximating things here, drawing a simple picture that gives us a little bit of insight into what's going on, okay? And it's a little more complicated than what I said before. Okay, the whole idea, the picture of the cube, you know, the rectangular solid, the picture you see over there, picture we drew last time, is still valid, but we have to look at it in a little more sophisticated way that we're not equipped to do. Still, you know, the various parts of this region, like the area between this one and the level curve here, where it's below, okay, or the volume of that little section there in the corner where it's below, and the volume of the part that's above, have important interpretations, okay, that we don't need to worry about right now. Just trying to give you a little bit of more of a geometric flavor. What we're going to talk about now is, you know, curves in space, okay, osculating curves, curvature, and all that stuff. But wanted to give you just a little blurb on that.